Okay, I'll just use it. Very happy that Sutomu defined generation with localizing and co-localizing subcategories in his talk. So I'll save a couple of minutes. Okay, so it's almost time now. Well, I'm not exactly in a position to thank someone for having me here, but I'll thank everyone who is here now, and it's been great. I mean, I had a lot of fun inviting all of you, and I'm very pleased that all of you are here now. So yeah, I'm the second speaker and also the organizer of this meeting. I'll be talking about injective generation of derived categories for group algebras. And I will be using the video from my phone and the audio from my iPad because the audio from my phone isn't working so well. So I don't think you will see a box with my video in it right next to the slides, but my video is there in the chat from the phone. All right. So okay, yeah, one last time. I'm perfectly audible right now, right?
Yes.
Okay.
Yeah.
Yeah. Okay. Okay. Thank you. Yeah. Thank you. All right. Okay. So today I'll be talking about that result by Jeremy Rickard that Sutomu mentioned towards the end of his talk, and I will show how a very similar result can be obtained for group algebras in a very different way. So to begin with, I'm going to have preliminaries of three different kinds. So there is preliminaries on, there will be some prelims on cohomological invariants, because in my world, the finitistic dimension is a cohomological invariant on the group algebra. And then I will also talk about the classes of groups that I'll be dealing with. And I had planned to talk about some preliminary knowledge on generation in triangulated categories, but fortunately, Sutomu did touch on that topic. So maybe I won't really talk about number 2 here. So to begin with, I'm going to fix a ring R. So this ring need not be commutative. And usually my commutative rings will be A. They will be denoted by A. So the first set of invariants that I'm going to define are splee and silp. They were introduced by Gedrich and Grunberg in the 80s. And I will talk about their uses later. So splee of a ring is defined as the supremum over the projective dimension of injective modules. Now, when Gedrich and Grunberg did their definitions, they used length instead of dimension. And that's why these acronyms are SPLI and SILP rather than SPDI and SIDP. So that is splee, and SILP is supremum over the injective dimension of projectives. So easy enough, but you'll see later why, I mean, these invariants are very useful. And then I'm going to define the finitistic dimension, but of course, Sutomu has defined that already in his talk. So the finitistic dimension over any ring is going to be the supremum over the projective dimension of those modules which have finite projective dimension. I used M1R to save space like this. And another invariant that I'm going to talk about is this K guy, K of a ring, but in this case, that ring has to be a group algebra. So if gamma is a group, so if gamma is a group and A is a commutative ring, so gamma is a group, A is a commutative ring, then K of A gamma will be defined as the supremum of over the projective dimension of all those modules, of all those A gamma modules, which have finite projective dimension over finite subgroups, over all finite subgroups, I mean. And you will see later on how this will be also a very useful invariant to have. And then I come to my first Gornstein cohomological dimension and the projective dimension of a certain specific module that I'm going to denote like this, B of gamma comma A. talk about B of gamma comma A first, because to talk about the Gaussian cohomological dimension, I'll have to talk about complete resolutions and Gaussian projectives. So B of gamma comma A is the module of all functions gamma to A. Can you please, can all non-speaker people unmute themselves? Yeah, thank you. So B of gamma comma A is the module of all functions gamma to A that are only allowed to take finitely many values. And it is very useful because actually, there is a classical construction now whereby you put a closed module category structure on the abelian module category, and then the homotopy category becomes equivalent to the stable module category. And in certain cases where you can define a stable module category over infinite groups, I'll talk about that later, if time permits, in a lot of detail. So if you're working over mod, let's say A gamma, and gamma is such an infinite group on which you can define a stable model category, then once you put a closed model category structure on it, the homotopy category becomes equivalent to the stable model category. This is a classical construction, and a lot of people in the audience here, actually, Henrik, Sergio, have written papers on problems related to like this concept, this construction. And so once you have done that, this is actually an old result by Benson. The cofibrant objects are exactly those modules, such that those modules M, such that this guy M tensor B gamma A is projective. And that is a key reason why this B gamma A guy is very useful and important. But we will see how, B gamma comma A and the projective dimension of B gamma comma A will play other kinds of roles for us, strictly as an invariant. And now we come to technically our final invariant, the Gorenstein cohomological dimension. So the Gorenstein cohomological dimension of a group gamma over a commutative ring A, much like the cohomological dimension, the standard cohomological dimension of a group gamma over A, is defined as the Gorenstein projective dimension of A of the trivial module A, the trivial A gamma module A. Now, what is a Gorenstein projective dimension? So from this point, I'll be writing the talk live. So to define the Gorenstein projective dimension, we first need to define Gorenstein projectives. Now, what are Gorenstein projectives? So to define Gorenstein projectives, we first need to define, just a minute. We need to define complete resolutions. You can just say totally access of projectives, but I'll still define complete resolution because that would be helpful. So what is a complete resolution? So let's say again, R is a ring. And so I'm looking at an acyclic complex I star, so let me not wait, let me dot I here. Wait a second. Let me write it like this. Fi di I in Z. So it's a double infinite acyclic complex of projectives. Well, a complete resolution of M, let's say. So let's say I'm defining complete resolution of a given module M, such that the following two conditions hold. So there exists an N such that for all, okay, I need to say something else actually. We fix a projective resolution. I don't need to say all these things, but I'm just trying to be a bit more formal here. So we fix a projective resolution of M. So with respect to this projective resolution, I'm defining my complete resolution. And actually we'll see later on, this with respect to business isn't really that important. So there exists an N such that for all small n bigger than this guy, the complete resolution, the first complex coincides with the second complex, as in this happens. What am I doing? Okay, no. Wasting too much time. Such that the first complex beyond n coincides with the second complex beyond n. This is standard enough. And the second point is the totally acyclic part. Second point is the totally acyclic part, which says that for any projective R module, hom of f star comma that projective module should again be acyclic. Now, why am I saying all this? Well, Gorenstein projectives, one way of defining them, are those modules that occur as kernels in complete resolutions. Well, most of the time, actually, it suffices to say that Gorenstein projectives are those modules that can be written as some syzygy of some syzygy of some module, but I'm not going to do that. Okay, now I may be wasting too much time on this. All right. And now, how do we define Gorenstein projective dimension? Well, Gorenstein projective dimension of any module M is defined as the minimal n such that there is a resolution of M by Gorenstein projective modules. So there is an exact sequence. Where each is Gorenstein projective. So now I have defined what it means to say that a module has certain Gorenstein projective dimension. And of course, if there is no such n, we will have to say that the Gorenstein projective dimension of our given module is infinite. And also, another thing that is worth noting here is that a module has finite Gorenstein projective dimension if and only if it admits a complete resolution, and that comes in handy a lot of times, especially when we're working over group algebras, where the group algebras say A gamma, where A is of finite global dimension. Okay. I don't need this because Tsutomu covered it. I'll spend some more time talking about these invariants, and then I will go into my result. So as I've mentioned in my abstract, my result is of the form that, okay, I'll just write it and then erase it here. So the result by Rickard that Tsutomu mentioned is that if R is a finite dimensional algebra over a field, and you look at the class of injective R modules as basically complexes concentrated in, let's say, degree 0, and you look at the derived and bounded category, if this happens, as in, well, I'm going to, so what this notation means is that this T guy is my big derived category, and log T inj R means the smallest localizing subcategory of dr containing the injectives. Again, as Tsutomu mentioned in his talk, localizing subcategory means triangulated subcategory closed under coproducts, direct sums. So Jeremy showed that if this happens, then the finitistic dimension of R has to be finite. So note that I'm not really differentiating between the big finitistic dimension and the small finitistic dimension, little finitistic dimension. So when people talk about the little finitistic dimension, they only consider finitely generated modules, and they don't restrict themselves to finitely generated modules when they talk about the big finitistic dimension. I'm not going to do that. I'm allowing all modules. So I'm just using pendim with a small f. So this is what Jeremy Rickard showed. And he also said that he doesn't know of any, there are no known cases, known, let's say, examples of R. And when I say R, I mean a finite dimensional algebra over a field where the above property is not true. I mean, there are cases where the finitistic dimension conjecture, as in this condition is true, but it is not known whether the previous condition is true. But there are no cases known where the first condition is not true. And number two, I mean, it is always nice to take a conjecture in representation theory in homological algebra and transfer it into derived category language. Like, well, I mean, famously, the Mackay correspondence was given that treatment, and there are many other cases. So that is always very exciting. And when I first saw this, actually, this is probably the paper went on the archive in 2018, but I heard a talk on this in 2017 by Jeremy. So when I first saw this, my initial reaction was, can we do something with the reverse holds? Because if the reverse holds, then we have a very neat equivalence, and we can just focus ourselves on checking the injective generation property. So what I'm going to do is, I'm going to replace R by a group algebra by A gamma, where A will be a commutative ring of finite global dimension, and gamma will be a group, an arbitrary, well, not an arbitrary, a group belonging to a large class of groups. I will define this large class very explicitly in a minute. I will show that in this setting, so of course, I mean, A gamma need not be a finite dimensional algebra over a field. I'll show that in this setting, finitistic dimension of A gamma being finite does indeed imply that the derived, well, I'm not going to write mod, the derived A gamma is generated like this by injective A gamma. Okay, this is what I'm going to do. So to get there, I need to talk about some results involving the finitistic dimension for group algebras, and then you will see how this result is proved. And that is why I spent a few minutes at the beginning talking about all these various invariants. Now coming back to the invariants for a minute, let me just say that SILP and SPLE, so this is a result due to Ioannis Emanuel and Olympia Teleli. Is Ioannis in the chat? No, I don't think so. From 2018. And this is something very, very helpful. So they prove that the following conditions are equivalent, where again, A is a commutative ring of finite global dimension, and gamma is any group. I mean, once you define some invariants, it is always interesting to wonder how they relate to each other, how like the behavior of one invariant influences the behavior of some other invariant. And in some cases, you do need this A to be Noetherian as well as commutative and of finite global dimension. And that is often a hindrance. We don't want that. And okay, like just as an example, one of the famous results proved by Goodrich and Grunberg in the very first paper where they introduced SILP, SPLE, and all these invariants was that if A is, I mean, they proved it over half algebra, so I'm going to give a group algebra version. If A is Noetherian commutative of global dimension, let's say T, and say gamma is any group, then SILP A gamma is smaller than or equal to SPLE A gamma plus T. This was proved in the paper by Goodrich and Grunberg, GG 86, I want to say. But the thing is, to this day, we don't know of any ring where SILP is finite, but SPLE is not finite, and vice versa. So like, this is a bummer because one would expect that something more general should be true, which is why this result by Emanuel and Teleli from 2018 was slightly more remarkable. And they proved that GCD being finite of the group, again, this means the trivial module has complete resolutions. And complete resolutions are key because that lets you define syzygy, inverse syzygy, which then becomes the suspension functor in the triangulated category structure that you put on the stable module category. I hope that makes sense. I'm not going to talk about stable module categories too much right now. So they showed that this is equivalent to saying that the Gorenstein projective dimension of any module should be finite. So this means any module has complete resolutions. Again, any module having complete resolutions is of course important if you're going to define your triangulated category structure on your stable module category, because again of the suspension factor. And they said if, well, the third point that is equivalent here is that in this case, SILP and SPLE coincide and they are finite. But again, note that we have still not proved this result, this GG result, for, like, we have still not been able to drop the Noetherian condition from this GG result. And the reason I'm saying all these things is because I want to talk about why these invariants are actually useful. And then comes, we get into prelims part 3. This part 2, we don't really need to do part 2 thanks to Sutomo. So what's happening in part 3 is I'm going to talk about a class of groups that I will that I have worked on, and then I'll talk about my own results. So there will be 2 classes of groups. Let's say, I mean, I'm not really that good with Roman numerals, but well, let's denote the first class by, okay, let's say A. So this class is type phi groups. If there are any Greek mathematicians in the chat, well, this was defined by Olympia Teleli in 2008 over Z. And the definition goes like this. Well, remember those 2 classes of modules that are defined at the beginning? This class and this class. So M1 is the class of all those modules that have finite projective dimension, like over A gamma. So gamma is any group and A is a commutative ring. So this definition for any commutative ring is, well, sort of new. I mean, Teleli didn't work with any commutative ring, she worked with Z. So M1 A gamma is the class of all those modules that have finite projective dimension as A gamma modules. And M2 A gamma is the class of all those modules, again, I mean, A gamma modules that have finite projective dimension over finite subgroups of gamma. So gamma is said to be of type phi over A if these 2 classes coincide. As in, for any module, it has finite projective dimension over the big group if and only if it has finite projective dimension over all finite subgroups. And I'm going to denote throughout this talk the class of all type phi groups over A by this symbol. Class of all type phi groups over A. So a very interesting property, a very useful property of this class is that, remember this invariant that I defined earlier? So this was the supremum over the projective dimension of those modules which had finite projective dimension over finite subgroups. Well, it turns out, and this is actually not that difficult to show, it turns out that a group is of type phi if and only if this guy is finite. It's not that difficult to show, but you do need A to be a finite global dimension here. This is not that difficult to show. But I would not be comfortable calling it my result, but I did prove it. As I said, it's not very difficult to show. And now I come to one of my main results that helped me prove this generation property for derived categories that I was mentioning earlier. This large class, this guy. Sorry, I mean this guy. So now the result that I proved, okay, no, I need to say some more about the classes of groups that I'm dealing with. So I've already defined F phi A now. Now I need to define a second class of groups, which are called Kropholler's hierarchy. There might be some people in the audience who have seen me give some talks on properties of derived categories of complexes of modules over groups in Kropholler's hierarchy. So I have done a lot of work on Kropholler's hierarchy. So how is this hierarchy defined? Well,
excuse me, can I ask a question just real quickly? Could you give some examples of groups?
Yeah. Right now, I'll do that right now. Actually, I want to define Kropholler's hierarchy, and then I'll give examples and both non-examples.
Okay, great, thanks.
Actually, I was thinking about that right now. Should I give examples before? Yeah, thank you. I'll do that right now. So I start with any class of groups. I don't know if there are many set theoreticians in the chat who will ask me to define a class properly, but any class of groups. And then I'm saying for any successor ordinal. No, sorry. Let's do this. H0x, the 0th level of the hierarchy, is the class that is exactly x, the class I'm starting with. Then for any successor ordinal alpha, I'm going to say a group is in H alpha x if and only if it acts on a finite dimensional contractible CW complex cellularly. Again, I just mean a permutational action essentially. Just that is enough for me, like permuting the cells cellularly with stabilizers in H alpha minus 1x. I can say alpha minus 1 because I said successor ordinal. And if alpha is a limit ordinal, then H alpha x is defined as the union over all H beta x, such that beta is strictly smaller than alpha. And I'm going to say gamma is in Hx if gamma, if gamma is in H some ordinal. Take this kind of liberties in a talk, some ordinal x. So this is Hx, and now I go into LHX. So this is the class of all groups, all of whose finitely generated subgroups are in Hx. Essentially groups that are locally Hx. So now examples and non-examples. I'm very thankful to the questioner who pointed this out, that I do need some examples here. Examples and non-examples. So example number 1, groups in type phi. So you can take groups with finite VCD, groups acting on trees with finite stabilizers, of course, groups with finite cohomological dimension, also groups with finite Braidon cohomological dimension. Bredown cohomological dimension, all these guys, and also H1F groups, where, okay, throughout this talk, F alpha A, as I've already said, will denote the class of type phi groups over A, and F will denote the class of finite groups. And H1F groups, all these guys are type phi. And so groups, examples of groups in the hierarchy, I'll come to a non-example right now, like in a minute. Examples of groups in the hierarchy. So H1F groups are these. And actually, very recently, Ian Leary, Peter Kropholler, and Tadeusz Januszkiewicz, I know how to spell it. Okay, did I get it right? Tadeusz Januszkiewicz, okay, I might be getting the spelling wrong. Anyway, very recently there was a paper, this is, I believe, from 2010, I want to say, Journal of Group Theory, where they showed that if you start with finite groups, then H1F is a strictly smaller class than H2F. I mean, H1F groups are, of course, H2M, that is not that difficult to show, but it's a strictly smaller class. And this goes all the way up to the first uncountable ordinal. And some examples of groups that are in one class but not in the other, well, free abelian groups give us nice examples. So free abelian groups of finite rank are in H1F or H1F. So of course they're also type phi. But free abelian groups of infinite rank, they're not of type phi. It's easy to show. Not of type phi, but they can be in the hierarchy. So for example, I want to get this absolutely correct. So just just give me a moment. So the free abelian group of rank T, free abelian group of rank T, where T is bigger than or equal to LF0, but strictly smaller than LF omega, where omega is the first infinite ordinal. So this guy is in H2F, but not in H1F, for example. And there are some other examples of groups that are not in the hierarchy at all. So for example, there is first Grigorchuk group. I don't want to define it right now. There is Richard Thompson's group, and these are also not of type phi. So the reason, and actually a referee made this comment recently for one of my papers. The referee said, this is a very convenient class to study invariants, and that is absolutely correct. I don't think that was the motivation behind introducing these classes. So if a group is in LHF phi A, this is my result. I will be quoting one other paper of mine, so I can call it P1, 2021. Then the projective dimension of this guy, remember this module of functions gamma to A that are only allowed finitely many values, is exactly equal to the GCD, Goretzka cohomological dimension of the group. And actually I make a conjecture that this should be true for all groups. And if we call this common value, let's say theta, then between theta and theta plus t, where t is the global dimension of A, lies the following. Lies the finitistic dimension of A gamma lies the supremum over the injective dimension of projective modules of A gamma lies pli A gamma and also this guy. There was a previous result like this by Jonathan Cornick and Peter Kropholler from the 90s, but there was a small mistake in there, and they didn't have the first condition, they had the second condition, and they were working over HF groups, but they did need Noetherian, and they forgot to mention that in the paper, so there was a small mistake, and we don't need Noetherian in this result. Now, I'll just mention one last conjecture and a related result from group cohomology, and then move to derived categories and like reap the harvest, exploit this result to get our desired generation result. So that last result is actually a conjecture. Well, it starts with a conjecture. Conjecture is of course not a result. So Olympia Telleli made it over Z, then I made it over any commutative ring. So the conjecture goes like this. So again, gamma is a group, any group, and A is a commutative ring of finite global dimension. Finite global dimension. Then the following should be equivalent. What are the following? Starting with GCD should be finite. I mean, GCD being finite is equivalent to this guy being finite. That should be equivalent to splee being finite. Basically name all the invariants, and they should all be what I call finite equivalent, as in one of them being finite should imply the other, any other invariant is also finite. Findim, finitistic dimension finite, and K finite. And of course, this is equivalent to saying the group is type 5. Did I miss anything? No, that's about it. And actually, when Telleli made the conjecture, she was studying over Z, and over Z you can add a extra condition, that is there exists a finite dimensional model for the classifying space of proper actions. If you don't know what this is, don't worry, of gamma. This is usually denoted by E under bar gamma. And yeah, so what my result shows is that this bit of the conjecture, where we're still just dealing with invariance, holds true when the group is in here. Obviously, because as you can see, like it follows obviously, any of them being finite is equivalent. I mean, if any of them is finite, from that information, you can derive that any other invariant should also be finite. And now we come to, and well, okay, sticking to cohomology one last time, you can say that for group algebras, this is a kind of finitistic dimension conjecture, because if I just focus on the finitistic dimension, I can say that the finitistic dimension being finite is equivalent to this guy being finite, that should be equivalent to this guy being finite, and that is a conjecture, obviously. And I can say that is a finitistic dimension conjecture if you want to put all your focus on this invariant. And also over Z, you can just focus on this guy and this guy and say that is a finitistic dimension conjecture for group algebras over Z. Now we come back to generation in derived categories. The thing to note here is that, well, first things first, very elementary lemma. Let's say T is a triangulated category of, well, I don't know, let's say T is either, say, derived category of bounded complexes over some ring or unbounded complexes, doesn't matter. If S is a triangulated subcategory of T, and let's say you're looking at a, well, a complex like this. I'm writing a cochain complex, but I mean, if you're working with chain complexes, this can also work. If you're looking at something like this, where each module, I mean, well, each xi, but that's not the module, where each xi is in S, then the whole complex is in S. The whole bounded complex is in S. This is very easy to show by induction. Actually, I believe this is in Jeremy's paper as well. But this is a very classical, like well-known result. We'll be using this. How? So what happens if SILP of a ring is finite? If SILP of a ring is finite, if you're now in the derived category, any projective module, so this means any projective module has finite injective dimension, right? This means any projective module, again in the derived category now, is quasi-isomorphic to a bounded complex of injectives. So if I look at, well, let's work with the unbounded category now. If we look at the smallest localizing subcategory generated by the projectives, it will be contained in the smallest localizing, well, yeah, smallest localizing, what am I saying? Smallest localizing subcategory of T containing the projectives. If I say generated, I can just say localizing subcategory generated. Yeah, so the smallest localizing subcategory of T containing the projectives should be contained in smallest localizing subcategory of T containing, well, bounded complexes of injectives. And from this lemma that I mentioned earlier, it is easy to show that this guy will be exactly equal to this guy. And it is well known actually that this guy is d mod r. I promised myself to not write mod. And this follows essentially from two facts, both of them quite basic. Number one is that localizing, okay, I shouldn't write this first. Well, number one is that every module has a projective resolution. And for most of you in the chat, this is probably quite straightforward and understandably so. Every module has a projective resolution. Number two, localizing subcategories are closed under homotopic limits. Or I can just say maybe, I don't know, direct limit of chain complexes. And also follows from taking, like homotopic limits about good truncations of complexes. So this is always exactly equal to dr. So when we have a situation like this, where this guy is all of dr, this guy will have to be all of dr. And now see, if R is a group algebra, if we are dealing with this, therefore it implies that this should imply that the injectives generate, basically. This is T, then log T. But how can we relate this to the finitistic dimension? And this is where, remember, we bring in our old class LHFIA. And oh, sorry, one small thing. Let's keep going back. So when I said the first Rickard group and the Richard Thompson group are not in the hierarchy, so the first Rickard group was known to be not in HF, and the Thompson group was known to be not in LHF. It is not still known whether LHF is strictly bigger than HF, but let's say it should be. And I was able to prove that you can replace HF by HF phi Q, and over here you can replace this by LHF phi A for any commutative ring of finite global dimension. Actually, no. I think Z, we need Z. But yeah, well, we have 5 more minutes. Actually, maybe I started a minute late. let's say I have 6 more minutes. Okay, so if gamma is here, then we know from my result that SILP is actually equal to the finitistic dimension. Okay, not always smaller than, but equal to finitistic dimension. Not always smaller than, because of course, if you take, as I was saying earlier, free abelian group of rank, I don't know, Aleph0, it will be in this class, but since it doesn't have, I mean, all these invariants will be infinite. Anyway, finitistic dimension finite implies SILP finite, and that implies our generation. But one remarkable thing here is that over group algebras, if the conjecture that I attributed to myself and Teleli is true, then SILP being finite should always be equivalent to the finitistic dimension being finite. So what it means is, if this conjecture is true, or if at least this little part of it is true, then the finitistic dimension being finite, implying the injective generation of the derived category, should always be true for all groups. And that is interesting. If Teleli, my conjecture is true, above generation property should always be true. So yeah, this is in a separate paper, like this treatment is in a separate paper. And I'm implementing the referee's comments now, so I'm not sure if it'll be out in journal version this year or next year. And finally, so when we say Kropholler's hierarchy, so let's say we are like this, let's say H1F. What happens is you get a finite length resolution of the trivial module. Let's say my trivial module is A. A has a finite length resolution by permutation modules with finite stabilizers. And the thing is, this follows exactly from the augmented cellular complex of the group action on the finite dimensional contractible complex, which is at the heart of the definition of H1F. And as you saw earlier, H1F is a very well behaved class. Why? Because H1F means that it is type phi. Type phi implies that, where did it go? Yeah, type phi implies that this guy should be finite. And if this guy is finite, the whole thing, all invariants are finite. So for H1F groups, for type phi groups, everything should be finite. And actually, well, I should have added one more condition here. It's that when you have Z in place of A, you have this, and also that this should be H1F. So it is expected that H1F should be F phi Z, expected, like conjecturally. So in the final couple of minutes of this talk, I'm going to say the following, that if in place of H1F, we just have this definition, and similarly, I mean, we build the whole hierarchy like this, it is very tempting to ask if all results that have been proved on the hierarchy can actually be proved for this algebraic hierarchy. And then it is tempting to ask if we can give a very triangulated category theoretic description of it. And one way to do that could be through derived generation. And this is in actually a third paper of mine, in a separate paper, I mean, that the derived generation. Okay, I'll end with this. Let's say for any, this guy is in HNX, then this guy, if this is T, then this is the smallest localizing subcategory containing lambda 0. Now, what is lambda 0? Lambda 0 means modules induced up from H0X subgroups. Similarly, lambda n would mean induced up from HNX subgroups. And so here, even if it is n, I can come all the way down to 0. And that is a boon. So the thing is, just this isn't enough to characterize H1F groups. Like if you have F, the class of finite groups in place of X. But if I tell you, this is a question, if I tell you that my group is in Hn, let's say F, and I tell you that this is satisfied, as in this thing is satisfied, lambda 0, modules induced up from finite subgroups, that class generates the whole derived category with coproducts, and I tell you that the injectives generate as well. So I give you 2 generation constraints. Can that imply something like, well, I'm not going to say something like, not going to say this, but I'm going to say something like the trivial A gamma module A having the old condition, finite resolution by, well, again, something like permutation modules of like with, let's say, finite stabilization, or not exactly this, but something like it. So yeah, so this is a nice area to end. So in gist, like the meat of the work that I presented today is on cohomological invariants. That is where all the heavy lifting is done. And then just as a clever corollary, we get the injective generation of a group algebras. And of course, even for finite dimensional algebras over fields, what Rickard works on, it is not known whether Rickard's injective generation is equivalent to the finitistic conjecture, finite dimensional conjecture holding true. But in this case, we don't know the other way, as in we don't know how we can go from the injective generation being true to showing the finitistic dimension should be finite. Anyway, thank you all for your attention.
Thank you.
Yeah, thank you all for your attention. Oh yeah, I forgot I'm the host, right? So, yeah, so if you have any questions, please feel free to ask me. Yes. Okay. Yeah, usually, I mean, I ask the speaker something, but since here the speaker and myself coincide. Anyway, yeah. And also, I should say, like, since Henrik is in the chat, a lot of what we know today about Gaussian projective dimensions is due to Henrik. A lot, almost like everything that I do. So yeah, thanks, Henrik, for that. Okay, if there are no questions. Yeah, sorry.
Someone is asking.
Oh, I didn't see. Yeah, please go on.
Yeah. So let me ask probably a stupid but a naive question. So you talked about, for example, CW complexes. But for example, are there some topologists who are working or interested in this type of topic?
Yes. Okay. So as I said, I'm only interested in, let's say, a permutational action, but there are people who worked on co-compact action. So the whole thing that I said, you just add the extra condition that the group must act co-compactly. And then there are some other invariants that one can work on to show that they are finite. Actually, there is one person that I know of who has done a lot of work in this area, Jang Hoon-jo. It's a Korean name, I get it wrong. Jang Hoon-jo. So he does the same hierarchy. He adds the condition that the groups must act co-compactly on the finite dimensional contractible complexes, and he calls it like Kropholler hierarchy is usually named H1 this, H2 that, and his hierarchy is K1, K2, like that. Actually, I don't think he was the first person to do it. I mean, I don't know, maybe Carlos Broto, Kichlu, like there are some other, like the Barcelona school, maybe also was interested in it, but they were interested in it for other reasons. They were interested to show finiteness properties of the cohomology ring to use for like stratification purposes, because at the end, like we are doing all these things to, like all the invariants are useful because you can go into the stable module category and for infinite groups, and that's like that's, I mean, you don't usually do stable module categories for infinite groups, and that's very helpful there. Yeah.
Okay, thanks.
Yeah. Okay. We have Sergio speaking in 30 minutes. Is that right? No, I mean 34 minutes, I think. Yeah. Yes, if there are no more questions now, I mean, our next talk will be Sergio's in about 33 minutes. I will be here if you want to hang around here and like speak to each other. Please feel free to do so. Or yeah.
Okay. See you in a moment.